During this session, I'm going to be building on the previous video's understanding of electromagnetic induction and developing Faraday's laws of induction from those initial experiments. So let's think back to what Faraday found out. Faraday found out that when there was a changing magnetic field, either by the magnet changing, the electromagnet changing, or the magnet moving, or a wire moving in a magnetic field, it induced electricity. Now, we'll look at a bit more detail now. But first of all, we'll introduce a term. Okay, the term is the magnetic flux. Now, magnetic flux describes a region is a measure of lines of magnetic force passing through that region. Okay, so the magnetic flux of an area tells you how many magnetic lines are passing through that region, and gives us some idea of, I guess, how much induction is going to take place. Okay, so magnetic flux is that. It's found out by multiplying the area by the magnetic field strength multiplied by cosine theta, and theta being the angle of movement between the magnetic field and the line drawn perpendicular to the area swept out. Okay, so it's just a way of compensating if things come in at an angle of sorts. Now, the unit of magnetic flux is the Weber, okay, and that's capital W and a B. Okay, so this idea of magnetic flux is going to be useful because obviously we're going to be looking at the change in the amount of magnetic field, so magnetic flux is a good starting point. Now, Faraday's law stated that the EMF induced in a circuit is directly proportional to the time rate of change of the magnetic flux through the circuit. Okay, so what we're saying is that we've got a magnetic flux and there needs to be a change over time of that magnetic flux. Okay, and that's shown mathematically as epsilon equals minus the change in magnetic flux divided by the change in time. Okay, so that's our starting point. Okay, we're going to work from there a little bit more detail. So if you think about this more carefully, for a single conductor in a magnetic flux, it can be seen that epsilon equals minus delta, in this case, a magnetic flux times delta times. That's the rate of change of flux density. Okay, so that's just the amount of change. Now, this is okay for a single conductor, but often we're talking about a number of conductors. In the case of a solenoid, there would be rings of inductors. So therefore we use a term called flux linkage, and all it is, it gives me that value n, which tells me how many coils there are. Okay, and this ends up giving me what is actually Faraday's law. The electromagnetic force is equal to the minus. Now the minus sign shows us that the EMF is always produced so to oppose the change in flux, and we'll talk about that later on with respect to Lenz's law. So multiplied by the rate of change of flux density. So that's the terminology we're going to use. Okay, and really what we're talking about is this rate of change of flux density is going to be change in values of Weber per second. So that's Faraday's law. So we know that EMF is induced when there's a change in the flux linking a conductor. Okay. So that term flux linking just comes from the fact that we're thinking about could be multiple coils. So Faraday's law makes the connection between the size of the induced EMF, how much EMF is formed, is proportional to the rate at which the flux is changing. And that flux is changing is all about the change in the magnetic field, or the location in the magnetic field, or so on and so forth. So finally it states that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux, or flux linkage. Okay, so flux linkage just applying to a situation when there's coils, perhaps in a solenoid. I'm going to link this back to when we're talking about the induction, and remember we came across a formula here of a single conductor in the magnetic flux density. It can be seen that, okay, So we know that the EMF is equal to minus the change in magnetic flux by the change in time, so the rate and change of flux density is known as. We also know that the EMF is equal to, if we're talking about a single conductor, which is in a straight perpendicular position to the magnetic field, is the magnetic field strength times the velocity times the length of the wire. And by combining these two things, we can see that the rate of change of flux density is equal to the magnetic field strength multiplied by the velocity multiplied by the length of the single conductor. Lenz's law. I kind of mentioned it earlier on. Now Lenz recognized that Faraday's law tells us about the size of induced EMF, but it doesn't really talk about direction. So direction comes up using Lenz's law. And Lenz recognized the direction of the induced EMF is such that it will try to oppose the change of flux that it is producing. This is probably best shown by a diagram. So let me show this as a diagram. Now we can see here, if we have a magnet which we're moving into a coil of wire, we will induce a current, but we can see here that the end of which of the solenoid, which the magnet is approaching, or the north end, is going to become a north pole. So that means it's going to resist in some way. Now this kind of makes sense if we're thinking about conservation of energy. So what happens is that resistive force which we have to overcome, that means that we're conserving energy, and that energy which we're putting in is then converted into electrical energy. And vice versa, when the magnet is moving out of this solenoid, what happens then is that we create a southern end of the coil, so it's going to cause an attraction to the north end of the magnet. So therefore, again, you're going to have to be doing some work, and that work is converted into electrical energy. So that's Lenz's law. A couple of questions here now. A search coil has 5,000 turns and has an area of 1.0 times 10 to the minus 4 meters squared. It is placed in a long current carrying coil as shown. Okay. So its face is 90 degrees to the lines of magnetic flux inside the coil. Okay, so remember we're thinking about the magnetic lines flowing through the middle of the coil here. What EMF is induced across the coil when the flux density inside it changes from 2.5 times 10 to the minus 3 to 1.3 times 10 to the minus 3 Tesla in 0.4 seconds. Okay? So think about how you can solve this, and let me take you through it. Now, it's the flux density linking the coil that changes. So that means the EMF is equal to, as we know, N, which is the number of turns, times by the change in flux density. Now we know that the change in flux here is going to be equal to the change in the magnetic field strength multiplied by the area. So if we know what the magnetic field strength is, and we actually also know the amount of time it takes, we can put these values in. So we've got 5,000 coils multiplied by 2.5 times 10 to the minus 3 minus 1.3 times 10 to the minus 3 Teslas. So that's the change in magnetic field strength times the area divided by the time it takes, and that gives me a final voltage, EMF, of 1.5 times 10 to the minus 3 volts. Okay, we'll go for another question now. In this case, a search coil has 2,500 turns and an area of 1.5 times 10 to the minus 4 meters squared. It's placed between the poles of a horseshoe magnet as shown, and the coil is rapidly pulled away from the field in 0.3 seconds. The average value of the EMF induced across the coil is 0.75 volts. Calculate the flux density between the poles of the magnet. Okay, so again, that the coil moves, the area linked by the flux changes. So in this case, we're kind of working backwards. We're trying to work out what the EMF is. Initially, we know here that, again, in this case, what we're doing is we're looking at the change in area, okay? Because it's going from an area 1.5 times 10 to the minus 4 meters squared to nothing. It's been moved away. So we're putting our numbers in. We know that the EMF is 0.75, and our unknown is B, the magnetic field strength. So therefore we put this through the calculations and work out that the magnetic field strength on this horseshoe magnet is 0.60 Tesla. One last question just to finish things off. Okay, an aeroplane with a wingspan of 40 meters moves at 200 meters per second. It flies horizontally through an area where there is a vertical component of the Earth's magnetic flux density is 5 times 10 to the minus 5 Tesla. Okay, so the magnetic field we're thinking about is that of the Earth. What is the induced EMF across the wingtips of the plane? So what we're imagining here is that this plane is similar to a single conductor traveling through a magnetic field, and it's traveling it through 200 meters per each second. So therefore, if we're treating the wingspan as a straight conductor, again we can go through our process. We know that it sweeps through 200 meters every 1 second, and so the area is going to be 40 times 200. That's the total area. That's going to be the change in area taking place. So in this case, we know we're talking about a single strip, so therefore n equals 1 straight away. And therefore the change in magnetic flux is going to be B times the change in area that it sweeps through. So B times the change in area divided by the time taken. We know it's going to be 1 second. So we've got 5 times 10 to the minus 5 Tesla times 400 meters times 200 meters divided by 1 gives me 0.4 volts of induced electromagnetic force. So there's some applications of Faraday's law, and hopefully that will be useful for you in the future.